Hey everyone, my name is Kelvin. I'm a developer and I make free tutorial content. If you like this kind of thing, consider subscribing and liking the video. And if you want to support me in other ways, you're always welcome to buy me a coffee. Okay, so today I want to do a crash course introductory Clojure type video. And I want to go over mostly everything that I know about Clojure, which isn't everything, but it should be a good enough foundation to get you started and feeling comfortable within the language itself. I'm also going to make the assumption that this isn't your first programming language, so we might speed through a few steps, but I think that's okay because for the most part, I don't think anyone starts with Clojure as their first programming language. So first things first, Clojure is a hosted language, so it needs to run on top of another language. And the main one that we need is Java. So you will need to have Java installed, and you can check by doing java-version. And here you can see that I have version 15 installed. Now, I don't think the version matters too much as long as it's above 8, I think is the cutoff for where Java starts being good. And also, don't worry, you don't need to know Java much to get the most of Clojure. Now, this is one of the things that I'm going to skip over. I'm not going to show how to install Java, mostly because I don't know how each time I install Java, it's always with a different method, so it's kind of up in the air what the right way is. But I will show what you need to install for Clojure, and it's going to be this command right here. So whatever your package manager is, so brew for Macs, on Linux, you can follow these steps down here, but depending on your distribution, you could also just do Clojure or Clojure tools Clojure. And the only extra tidbit that you need to know is that you want to have RLWrap installed as well. And the only thing about RLWrap is that instead of typing Clojure into your command line, you can just type in CLJ, and this will start up a running REPL. Now, if you're inside of the Clojure world for any bit of time, the REPL is going to be basically your best friend. And if you don't know, it's this prompt here where it could read in Clojure code, evaluate it, print it, and it runs in a loop, so it'll always do another prompt right after. So that's where the name REPL comes from. Read, eval, print loop. Now let's start with hello world to get a sense of the Clojure syntax. You'll see that we opened up parentheses, or I'm going to call them parens for the rest of the video, where the first word is the function. So this is print line, followed by the argument of the string hello world. And this will return us with nil, which is the equivalent of null inside of Clojure. And that's basically saying no value. But it also prints out hello world to the console, or the shell, or the prompt, whatever you want to call it. Now, the next thing you want to know is that each set of parens and things inside of it is called a form. Now, the next thing that I want to show is, let's do some math, because in Clojure, it's a little different than what you're used to. So we use prefix notation instead of infix notation. So the operation is on the front, so prefixed. And this is because all the operations, the arithmetic operations, are functions. So they don't behave any different than other functions. So this is 1 plus 1, which is 2. But one of the benefits of prefix notation is that you can have any amount of arguments and it'll all add up together. So this is 15, even though we're just adding 1, 2, 3, 4, and 5. Now the next part of forms is that they're evaluated from inside to out. So if we were to open up another form inside of this form, and let's just say that we multiply 2 and 2, that should give us 4, which will then be added to 3 and 3. So this we should expect to come out as 10. So that's the basics of the Clojure syntax. Now that we've gone over that, let's exit this REPL and open up a editor. Actually, let me open up VS Code. Okay, so I'm downloading VS Code just for this video. That's okay. Now let's open it up. Yes, don't care, don't care. So the reason why I want to show VS Code here is because I think it's the best beginner editor for getting to Clojure, mainly because of the Calva extension here. And I'm just going to do a quick overview of how to use it. But then after that, I'm going to switch to Vim, which is the editor that I'm most comfortable with, for the rest of the video. Now, I'm just going to make a new file. I don't know what the keyboard shortcuts are, so I'm just going to use the command palette. But the one command that you're going to definitely want to know is jacking in. And this will start a REPL and connect the editor to it. The other one that you could also use is to connect to a running REPL. So in case that you already have your REPL open in the terminal, you can connect to that one without doing the jacking in, which is starting a new one. But let's just jack in for now. No supported types. Oh, right. So I guess we need to do a little bit of configuration. So deps.edn, and I'll just add an empty map for now. So just curly brackets. Okay, that's good enough. All right, back to what I was saying. Let's now jack in, and we're using a deps.edn file, even though it's empty. Okay, so what we have now is a REPL window on the right-hand side. And you can use this side the same way you've been using your REPL before. So if we do a print line, hello, I want to press enter at the end of the form, we'll get hello, and this time we have a new line because I accidentally added that, but that's okay. But we also have the return type of nil. We can also do 1 + 1, and we get the answer of 2. Now, let's go into our file. This is one of the many reasons that people like using Clojure so much, and that's because you can send in this code into the REPL. So imagine copy and pasting your entire file into a running REPL and getting the answer. So we want to evaluate this form, and I think evaluate current form should be the right command. And we get our answer of 6 here, as well as a pseudo prompt of 6. We can't actually select this, so it's not real text, it's virtual text. Now I would suggest to play around with Calva. There's other commands that you can use. So you could evaluate from the start of the file or the start of the list, the top level form. But essentially that's all you need to know in terms of editor integration. When we do an evaluation, we're taking something from our file and sending it straight to the REPL, so we can just get the answer right away. So if you're coming from the world of C# or Java, imagine having a running debugger that updates with every code change. A lot like how JavaScript has a hot reloadable browser console. All right, with that out of the way, let's exit VS Code and go straight into Vim. Actually, before that, we need to start up another REPL. And this one's a little special because it adds a connection middleware so that we could connect our editor to our REPL. This is a little bit more advanced, so I'm not going to cover it right now, maybe a little later, but all you need to know for this is that I need this to connect Vim to a REPL. We can now open up Vim, and if we go to the file that we were working on, which is user.clj, you'll notice that I get this little REPL window that says that I'm now connected. And if you're wondering, the plugin that I'm using for Clojure REPL stuff is called Clojure. And just like Calva, I can send in the form from our header straight into the REPL. To make things a little easier, we could also open this up into another tab or a window where we could just write other code. Okay, let's get back to basics and cover some stuff. The first of which is these semicolons is how you could write comments inside of Clojure. So this is the normal comments that you're used to, like / in JavaScript or the hash sign in Python. But there's another comment that you can use, which is the comment form. And the reason to use this specifically instead of the normal comment is because whenever we make a change to the file, we're going to want to evaluate the entire file like this, and it's going to send in everything from the file into the REPL. And sometimes we don't want that because we don't want to do actual operations. So you see the 6 up here. That's coming from the first form that we made to add everything together. So generally, when you want to play with code that you don't actually want to commit, you'll add it into a comment form like this. Now, previously, when we were playing with the REPL, we worked with strings and also numeric types. I believe we only worked with integers, but there are other different types. So we can do a floating point number, and this, I believe, is a double. So they're called doubles. Most of the primitive types are going to be coming from Java. So if we add in false, we should get a Java Boolean. But then things like nil is going to be Clojure specific. So nil is, once again, the no value type. And in many functional programming languages, the no value type is somewhat different from a null type in other languages, specifically because it's reserved for actually having no value instead of what null is used for in other languages, which is no value or something went wrong. But functional programming kind of makes it a lot more strict in that if something went wrong, you get an error type instead. but that's kind of just a side. It's not really necessary for beginners at the moment. Those are the primitive types. There is one more thing to note. Strings, you need to use double quotes because a single quote is actually special. It has syntactic meaning inside of Clojure. So a quote mark basically means it tells the interpreter or the reader to ignore evaluating the next thing. So this something here is called a symbol. And we can't evaluate it here because it's not in something, but it's a value that represents a variable name. Speaking of variables, the def function or macro is how you could hold a value. So here we'll do temp and we'll give it the string of string, right? You're going to need to evaluate this so that the REPL has the memory or the state of this variable, or var is what it's actually called. So let me add that, vars. And then you can evaluate it here and you get the string. Now back to changing this to a symbol. If we evaluate this, we get something back, right? But notice that it doesn't have the quote mark. And that's because when reading by the interpreter, it needs to use the quote mark to skip evaluation. But after being evaluated in the REPL, you just get the raw value, which is the symbol of something. And this leads to the next question is, if the quote mark is for symbols, then how do you define a character? And that is actually with the backslash. So you could do C for character. And if you evaluate temp here, you get the character of C. Okay, so I think that covers enough about the simple basic types. Let's go into the more complicated types. So all the types that compose other things together. And the first one I want to show is a vector. So let's just hold 1, 2, and 3. And here you get the vector, which is denoted by square brackets of 1, 2, and 3. You can also write it out raw with the square brackets in your file as well. And when you evaluate it, you also get 1, 2, and 3. So vectors is the main list type inside of Clojure. Unlike Java, it's a little bit more dynamic. You can also hold strings and characters, and all of it works as you would expect it. So this is a list of things, but there's a different data structure or data type called a list, which is similar, except it's denoted by parentheses. And this is where we need the quote mark again, because to write it raw inside of your file, you need to use the quote mark. If you were to try to write it without it, it's going to expect this to be a form. This is invalid because 1 is not a function, so it can't evaluate this. And this is where the term lisp comes from, which is short for Lisp programming. So everything inside of your program is a list. So it's a list of instructions where the first thing is usually a function followed by all of the arguments. And this leads into the giant meme inside of Clojure, which is everything is just data. So even your code is data. Data. All right, anyways. So now we need to actually show what the difference between a vector and a list is, because essentially most of the things you use them for, they can be used interchangeably. But here's the difference. Let me wrap this in deps so that I can show you this. So now we have temp vector and temp list defined so that we could use them for a few other things. So the biggest difference is the underlying implementation of it inside of Java. They're both constructed as linked lists, but one's implemented as a stack and the other one's implemented as a queue. So the function to add to the list is conj. And let's just add the number 10. And based on which one that we want to evaluate, 10 will go into the front or the back. So for temp vector, it goes into the end of the list, and for temp list, it goes to the front. And this leads into the concept of polymorphism inside of Clojure, because even though these are two distinct types, they're treated as the same for certain functions, and the type is a collection. So a list is a collection, and a vector is also a collection. But there is also another root or parent type called a seek, and this is where they're different. So a list is a seek, but a vector is not. But even though a vector is not a seek, you can transform it into a seek with this function. Out the other side, you get a list. And I don't think it's really necessary to understand the difference between collections, seeks, and all the other things. All you need to know is these are intermediate types that allow functions to be called on any form of these things. An example is first, where we get the first value of whatever it is. So for temp vector, we should get 1. And then also for temp list, we also get one. And this goes for all other functions that you expect to work on a list type. So second, we'll give you 2 from both the list and the vector, like so. And this form of polymorphism is really useful because otherwise you would have to have something like list first or vector first. And this actually does exist in another language. In Haskell, there's fmap for functors and then mmap for monads, even though they're all implementing the map function, just with different types. But in Clojure, you don't have to worry about that, so that's nice. This is also a good time to go to the Clojure docs. Since Clojure is a functional programming language, the core library has hundreds of functions that are basically used for anything. So we saw that we have first and second, and I don't think we have a third, but we do have last, which will give the last thing in the collection. And we also have rest, which will return the collection without the very first thing. So the rest of the list. All right, let's go to the next data structure, which is a set. So there's not really much to say about a set. It takes in a list type, so any collection, and returns a set, which is denoted by a hash symbol and then curly brackets of everything but the duplicates are removed. So here we have 1 3, even though we sent in a list with multiple 3s, and then we could add more 3s, and we still get the same thing. And of course, you could write it inside of your file like so, and evaluate it as such, and you'll still get the same result. I'm unsure how the ordering works because you'll see that this is not in the usual numeric order. 3 for some reason is the second value, but that's okay. Now, there's not really much to say about sets. They're not used all that much as values. They're more used as a function, like we did on the very first line, to remove all the duplicates. But these are still considered collections, so you can still do first and second to get the value from the set. But once again, the order is a little different from a list and vector, so it might not be what you expect. Now, let's go on to the final data structure that's arguably the most important one, the one that you'll see the most, and that is a hash map. So let's start with the function that makes a hash map. And what a hash map is the equivalent of a JSON object or a dictionary, where you have pairs of keys and values. And here we're going to make a hash map of 2 pairs, the A being the key to the value of 1, and B being the key to the value of 2. And it's denoted by curly brackets. And this comma is not actually necessary. It's just there to make it a little easier to read. And I don't think I mentioned this, but commas in Clojure are just white space. So this is the same thing. And to prove it, I'm going to add it into a def and evaluate this, and we'll get the same answer. And also just to show how ridiculous it is that commas are white space, this with the commas in front, and we just put a bunch of commas here, is valid Clojure code. Just please don't write like this. Let's go a little bit more in depth with maps. So they're denoted by curly brackets, and we could have anything as the key. So currently we're using strings, and we have anything as the values. So this is where we could have more complicated data structures, because now we could have a vector as a value, and inside the vector we could also have another map like this. And if we evaluate this, it comes out as expected. Now, typically we don't use strings as the keys. Instead, we use what are called keywords. And starting out, the only real thing you need to know about keywords is, well, first, they start with a colon, and then you can add any key after that. Also, each key is somewhat of a unique identifier for the file, and they're essentially an easier way to write a symbol. Technically, these two are different data types, but you'll see keywords almost everywhere. And when I say anywhere, I mean they don't always have to be the key. They could also be the value, like this. And let me just evaluate this so that you can see that it comes out. Now, I also want to show that if you add another key with the same name, so some key again, and we'll just add 666. Why not? We'll get a duplicate key error. Also, I think I skipped this, but you'll also get the duplicate key error for sets if you try to write it raw like this. So let's get rid of that. And now let's go into the functions that you will use to deal with maps. So the first one we're going to use is get. So get, you can provide the map, and this time let's say that we want to get some key. When we evaluate this, we get the single value for that key, so the slice of the map. But let's say we have a nested thing, and here we have another key, and finally let's do the value, and it's just going to be a string. So first, we can try to get the nested thing first, and then wrap this to get another key. This way we get the specific value. But there's another function that we can use, which is getIn, where we provide the map, and then a vector of the path to the actual value that we want. So the first one is nested thing, followed by another key. And then evaluating this, we'll get the same value. All right, now let's go into the mutation functions that we use, so mutations. The first one is assoc, or associate. This is where we can provide the map, a new key, and a new value. And this function will return the new map with the key and value that we added. Similarly, we also have assocIn, where we can provide the path inside of the map, and then finally the value that we want to add into the map. Now you'll see that nested thing has our original another key, as well as the new key value that we add. And finally, this soak. This one we just have to provide the key, but it'll get rid of the entire slice at that map key thing. So now we have the original thing where it's just strings and some key, and we got rid of the nested thing, got rid of the entire nested thing. Now you may have noticed that the original temp map is still the same. What these functions do is return a new object, so a new map in this case, with all the modifications from these functions. And this is a thing that happens across all of the values inside of Clojure, because it's one of the principles of functional programming in general, immutable values. But because it's part of the language, we also get something called referential transparency. And let me clean this up a little bit so that's a little better. So what this means is that we could set an equality of temp map, and then the raw value of this entire thing. Like I'm going to copy and paste this, and this equality will be true because this is not a variable in the traditional sense. It's not pointing to a memory address. It's actually pointing to the value. So it'll be false if we change something like some value being without the E, or if this nested thing is not nested. Both of those are false because the value that we're comparing is a different value completely. In a less abstract way, what we're essentially doing is saying, is 2 equal to 2? If so, it's true. But is 2 equal to 3? No. And this is one of the benefits of functional programming. These variables don't change within an operation. So you could, in your brain, you could substitute it with the value that they're holding. Okay, so we went through all the important data types. Let's now go into writing functions. We've used functions, but we haven't written one of our own. Let's start with an anonymous function. So a function that has no name, so that we could explore the anatomy of the function form. So the first thing is going to be the function, or the fn function. I guess you could also call this a macro. And then it's going to be followed by a vector. And this is where you could specify the arguments that you want. So let's say that we have a and b. And now this function has access to 2 arguments that needs to be passed in. And then finally, the last part is the function body, where we can do anything with the arguments that have been supplied. So here, let's just add a and b together. Now, functions are just values inside of Clojure, so we could treat this the same as all the other data types that we've been using. So we could put it inside of a def, and then give it a name with a symbol. So let's just call this add, or actually let's call it add2, just to be very precise. Another note about the function body is that the return of the entire function is the very last form. So if you were to add another form inside of here to do something like print a and b, you could do that, and this won't actually change the return type in any way. So let's evaluate this def so that it's inside of our REPL. And then we could call it by doing add2 and then providing any 2 arbitrary numbers. So let's do 1 and 3, and this should give us 4, which it does. But it also has the print of 1 and 3, which is this little comment thing here. But once again, the print line has no impact on the actual return of the value or of the function. Now I've written the function this way just to demonstrate that a function is a value inside of Clojure, but there's a shorthand way of doing it, and we have the def.edn function or macro. And let's just call this add2 again, which is then followed by the argument list, or vector, I mean. So we can do a and b again, and then we're gonna write down the same function body that we had earlier. Now, optionally, before the argument list, you could have a docstring, and this one is purely for documentation reasons. But you could do add two numbers together. That way, if you try to get the document of the word, or the type hint, or I think that's right what it's called, but you get a little thing that gives you some information about how this function is meant to be used. Now, the way that we wrote this function, it specifically wants two arguments. So if we get rid of one of these, we'll get an error. And if we also add another one, we'll also get an error if we try to evaluate this. But earlier, we've seen that plus function doesn't have that limit where we could just add an arbitrary amount of arguments altogether. And there's two ways to achieve this. So let's define another function that I'll just call add more. The first way to do this is to wrap each inner function, where the first thing of the form is the argument list, and then you just have the normal function body following it, as you would expect. But this way, we can have another function body here that'll behave differently based on the amount of arguments that are provided. So here this function now is able to add two numbers together or three numbers together. So to show that, we could do add more 1, 2, and that works, and which gives us 3. And we can also do add more 1, 2, and 3, and this will give us 6. But this will be pretty annoying because as soon as we add a fourth argument, it's all of a sudden errors out, which means we have to add another form for each subsequent argument. And that is way too much work. Instead of doing it this way, you can provide an argument list that starts with an and then give an identifier, which I'm calling x. So it'll just take all of the rest of the arguments and put it inside of a vector. And instead of adding all of them together, I'm just gonna return x so that we can see what is being provided. So add more with 1 and 2 will give us a list of 1 and 2. And then add more with 1, 2, 3, and 4 will give us a list of those 4 items. So to expand on what those methods are, this is using the rest of the argument list. And then the other thing, which I wish I did not delete, but A and B, A, B, and C. All right, this is called multi-arity. And multi-arity could give a lot more possibilities than just making it possible for more arguments. You can actually make a function that changes behavior based on how many arguments there are. So let's say we do a function that's just idk, so I don't know, and given 2 arguments, we'll add those together, but if we have 3 arguments, we'll multiply all those together. This function, probably not very useful, but it does demonstrate that we could completely change the behavior based on the argument list. Adding 1 and 2 together gives us 3, and then multiplying 1, 2, and 4 together will give us 8. Let's clean this up and go on to the next concept inside of functions. So the argument here is inside of what's called a closure. So this is with an S, not with a J. And what that means is that these bindings only exist within the function. So it's a scope feature. So because of that, we need to explain that def is the global scope, which means if we were to put in here def A and to A, this is technically a bad practice because it's an inline def, but it means that if we do add 2, and we just do 2 and 2, we can also evaluate because we put in the first argument into the global scope of the REPL namespace, but this is bad. A way around that is that we know we have function scope with the argument list, but we have something else called a let binding. And to demonstrate that, let's wrap this in a let, and let's say we have C, right? So C is going to be our new def, our new var that we're creating. And here I'll just do A and B, and we'll just return C. So the way the let works is that you provided a vector much like the function argument list, except it's inside of pairs, so you could think of it as tuples, where the left side is the identifier, the symbol that you want it to call it by, and then the right side is the actual value that you want to put inside. So here we're putting the result of a plus b into c, and then we'll return c from the function. So if we do 2 and 2, or let's do 2 and 3 this time, the function still remains the same behavior, but C doesn't exist inside the global namespace because it only exists inside of the let binding. And I wanted to go over Clojure's with functions because it's a very similar concept, but a let binding doesn't have to be in a function. So let's say A is 3 plus 3, and B is the multiplication of 8 and 9. And then we'll just return or A plus B here. And you can evaluate this let binding, which will give us the result of 78, but it's not inside of a function of any kind. It's just inside its own closure. Usually you won't see a let binding outside of a function unless you're using it to play with the REPL, but it is important to understand. So a quick aside on naming conventions. So far you've seen that we write our variables as kebab case, so using dash snake case. And symbol names don't really have a lot of restrictions. It's that you can't use the quote mark and you also can't use the hash mark. But other than that, you can use basically anything as a symbol name. So this could technically be a variable name if you really wanted to. In fact, the most hilarious example of this is that this is an open source function name, although it's a parody from every Clojure talk ever. And if you haven't seen this talk, I highly recommend it because it's a pretty good one. But going back, there are some guidelines on what kind of variable names are good for functions. And these are some simple guidelines. So names that end with a question mark are generally Boolean functions. So something like even 3 is false and 4 is true. And this is actually from the core library. But then next is for data transformations. So we've already seen a list going into a set. And this is a very small example, but if we do this and do list sets, and we'll provide like 1, 2, 2, 3, or 4, whatever, we'll get the set of 1, 4, and 2. And usually out in the wild, transformation functions will always have an arrow in between where it goes from the source to the results. And we haven't really covered mutations yet, but names that end with a exclamation point are usually non-pure functions with side effects. So things that are stateful, that changes something in the system, or even outside the system, are usually denoted with an exclamation point. And then finally, names that end with a star, they're kind of up in the air. They mean what the library maintainer wants it to mean. So sometimes it means it's exposed private functions, so things that you're not supposed to touch, but you can if you really want to. And then sometimes it means a deeper level of implementation. For example, if you're dealing with a database library, I know one of them has a star for being able to write raw SQL code, I think. I've seen that before. But at the end of the day, it's whatever they want it to mean. A star just means it's special in some way. And before we go on, I think it would be a good idea to show an example of another Boolean function. So usually when you're learning programming, you try to implement even or odd with the mod function, but they're provided to you by the core library, so I'm not gonna do that. Also for reference, mod you have to spell out because percent actually means something else, and not you have to spell out because the exclamation point doesn't work. That's just a quirk, but these are actual functions that you need to call inside of a form. Okay, so instead we're gonna implement a function called isSumEven. And it's going to be an evolution of our add2 function. So I'm only going to add 2 arguments, so a and b again. And we know that we're going to start with adding a and b. But this time we'll wrap it with even and try calling it with 5 and 6. And this should give us false. And then if we do 5 and 5, it's true because the first one was 11 and this one is 10. that being the sum. But then we could go beyond this, mostly because I wanted to show off that if is a very valuable function. And the way if works is the first argument is the condition. So we have the even here. The second argument is the truth clause, and then the one after that is the false clause. So here, let's do A and B. So if the sum is even, we're just print out the sum. And then if it's false, we could return a string saying not even. So now if we call is sum even on 4 and 5, we get not even. But if we do 5 and 5, we should get 10. Now I also want to show the counterpart to if, and that is when. And when is similar to if, except you use when you don't care about the false clause. So what happens when it is false? You get nil. So no value comes back, but you still get 10 for the truth clause. And finally, the last kind of function that I want to show off are loops, because loops or iterations in general are one of the most important things in programming. However, in a functional language, it's a little different in that if you need to use it inside of a function, the go-to way of doing that is recursion. Because if you think about it, a for loop and a while loop depends on mutations, and we're not about mutations, so we're going to use recursion. So let's do a simple recursive thing. So let's go with the factorial function, because that's an easy recursion thing to wrap your head around. So a factorial needs a number, and the recursive loop for a factorial is n multiplied by the factorial of n minus 1, so 1 less. And we can use decrement of n. But of course, we need a case to actually exit the loop. So we'll wrap this in an if n is greater than 1, I believe. Yeah, so if n is greater than 1, we'll do the loop. Otherwise, we'll return 1. Let's see if this works. And let's go with 0. The if statement works. And let's go with 3. That's correct. 5? How big can I go before it goes crazy? 7, 8. Yeah, that's a big number. Also, to prove it to you, decrement is just 1 minus the number, and its sister increment is 1 plus the number. These are little useful functions that you'll end up using more than you think. Now, there is another way to do iterations and loops, and that is to just use a function. And the one that we're going to go over is map. And let's just iterate through some random list of numbers. Now, this is also going to be a segue to higher order functions, so I'm going to clean this up and change this little title thing to higher order functions. What a higher order function is a function that either takes a function as an argument or it returns a brand new function. The big three being map, filter, and reduce. And then all other functions that kind of do the same thing are based on these three. And there's a lot, so if you go into the documentation, there's stuff like mapv, mapkv. Is it this one? No, it's not. I think there's also mapcat. Yeah, there's a lot. But back on topic, the first argument here is going to be any arbitrary function. And let's just go with the increment function that we used earlier. So if we evaluate this, we should get a list where each item has been incremented by 1, and the list that comes back is 2, 3, 4, 5, and 6. Now typically the function that is passed in is referred to as the predicate function, and this could be anything. In fact, you could define your own function here, and let's space this out so it's easier to read. And we can put in something like, instead of doing increment, let's just multiply it by 3, because that's just a random thing that we can do. And then if we map through the list, we should get all the multiples of 3. Now, I know I skipped this, but there's a shorthand way of creating a lambda function or an anonymous function. Lambda is anonymous function. That's just some terminology that you'll have to get used to because people end up using these two a lot and interchangeably. But the shorthand for writing a function is we're going to write it with a hash sign in front and then just the function body. So here is going to be the same function, and then also the percent sign is going to be the arguments that are passed in. So this is the shorthand version for the same functionality that we did earlier. So we still get the same result. Now let's do a filter, and the function here I'm going to pass in is even, and we'll provide the same list. So 1, 2, 3, 4, and 5, and this time it's going to filter out everything that doesn't satisfy the condition So 2 and 4 is the only thing that's left over. And here for the filter function, the predicate needs to return a Boolean. So we could provide a function that just returns a Boolean. So let's just say that we're expecting only 3. If we filter this, we'll get a list with only 1 item in it, and that is of 3. Now reduce is a little more complicated. In fact, I need to check the documentation. So it goes function, then collection, or function, then value, then collection. And if I'm correct, value is the initial value. So let's start with the collection that we're going to use. It's going to be the same thing. So 1, 2, 3, 4, and 5. And the initial value is going to be an empty vector. Now the predicate function here has 2 arguments. And that's why we're not going to use the shorthand, because we need both the arguments. Now I always need to look this up because I don't remember what order it is. Okay. Now I remember. Okay, so the first argument is the accumulator, and the second one is the current. So the accumulator is this initial value of an empty list, and then the current value is just going to go from 1 to 2 to 3 to 4 to 5. Now I don't know what to do to make this fancy, so actually, you know what? Let's change this to a map. That way we can be a little fancy. So I think what I'm going to do is do an assoc on the accumulator at the key of whatever the current is, and give it the value of the current. So if you're confused by what this is trying to do, essentially I want something that's going to be like 1, 1, and then 2, 2, and 3, and 3. So it's still simple in the case that it's easy to understand how reduce works. It's just a little fancy because now we're dealing with maps. We're turning the vector into a map. And let's see if that works. And it does, so, you know, that's cool. Now, as mentioned, these are the big 3. These are the ones that you should know and lean on the most, but sometimes there are other functions. I believe for a filter, we have find, and instead of providing a predicate function, you could also provide a set, right? Is that right? Oh no, this is the wrong one. I think it's sum. Yeah, so this will return the 1 back, the item that has 1. Let me add numbers out of order so that you'll know it's not the index that we're getting back, but the value. So we're getting the value of 1. And sum is kind of a riff on filter. It's based on filter, but it's a little more narrow and specific. And a lot of the higher order functions that are provided by the core library are a lot like this. So I know reduce, there's a reduce KV, allows the current value to be key value, and then it expects a vector of maps. So 1, 2, with like stuff in it. That's a little more complex and advanced, but you will stumble upon it eventually. Now the other side of higher order functions is when they return a new value, and it uses closures for that. So closures with an S, closures, which is, you know, the inner scope of the function. So let's quickly define something. And let's go with, yeah, let's do add to, as in, you know, that's a bad name. Let's go with sum with. So we're going to create a function that does an addition. And this should be x, and we'll return where it's x plus y. This might be a little confusing if you're new to this, but if we were to do sum with and go with 3, what comes back is a function. And the function explicitly means, so this will be sum with 3, and then you provide another variable or another number, which will be 3 plus x. Or in this case, this will be y. We could put this in a def and just call add to 3, and then call add to 3. And let's give it 4, which should give us 7, which it does. Typically, that's how you would see these being used, but there are times when you'll just do it raw. So we'll do sum with 5. And remember, it resolves inside out. And we want the result of this to be the first part of this form. And we'll add 6 here. And this will give us 11, because this part will be replaced with that new function that we created. This is more on the principle of functional programming and how you can use and leverage functions as values. Because right here, we're just creating a function and then storing it as a value so that we can use it later. This as a topic can go much further, because in here, we could have stateful things like access to a database or state. And that's why we would create a def here so that we could use it later when we do have a connection to the database. And that is one of the powers of closures. But there are other concepts which I don't want to go into here, like currying and partial application and stuff, because that's kind of beyond the scope of just knowing the language, because those concepts carry over to other program or other functional languages. And here we're kind of just trying to learn Clojure as the language and get up to speed with working knowledge. And speaking of which, we are finally at a point where we could write a real Clojure file. So now we can go into our deps.edn file and do a little bit of configuration. So now you'll notice that deps.edn is just a map, and there's 3 sections. One is the source paths, so we're going to just set it as source. The next is our dependencies, and this is just going to be a map of each possible dependency that we want to add to our project. The core library itself is optional, but I'm adding it here so that you can see the structure of the deps map. And I think we're on 110.3. I may be wrong, but pretty sure that's correct. And then finally, we have our aliases, and this is a map of stuff. The only alias that I'm going to add here is run, and that needs main options. You can look up more on the deps.edn Clojure documentation, but the main ops is basically the arguments that you want to pass into it as if this was a command line. So -m is going to be the main function. And then finally, the namespace of our, so this is going to be app.core. We haven't covered namespaces yet. That's because that is the very next thing. So with that, let's create our app.core file. So we need a source directory, and inside of that, we have app, which is the name of our application, and then core, which is the name of our file, .clj. Now, to facilitate the -m main option that we just created, we need a main function. Now, this could be anything. So we'll start with hello world, but with all of that set, we can now, this is the wrong place. Here we go. That's where I am. Okay, we can now run our alias with the Clojure command line. So that will be -m, followed by the alias name that we gave it, which is :run. Too many arguments to oh, that's because this is supposed to be a def-n. All right, let's try this again. And there's our hello world. All right, now let's explain what a namespace is. So a namespace is basically the equivalent of a file name. It's how Clojure separates all of our code in a meaningful way. And let's say we have another file, which I'll call otherfile.clj. Oh yeah, a note here, this needs to be underscore cased. So let me fix that. And that's because the file name is read by Java, but inside of the file, you could change the underscore to dashes. Inside the file, the namespace is read by Clojure. Hopefully that makes sense. And here, I'll just write something. Let's do from other file, and we'll just return true for now. But I'm gonna evaluate this entire file. Then if we go back to core, we could require it by doing require, and then inside of the vector, we'll do app.otherfile. Let's stay there for now. So let's evaluate this file, and I'm going to open up a comment block or a comment form, and I'll call the function from the other file. So app.otherfile / from other file. And remember, all this does is return true. Now you can also do other stuff inside of this vector by providing keywords. So as we'll give it an alias. So if we now evaluate the file again, so it's updated, we could do of from other file, and this will also return true. And finally, the last thing that we could do from the require macro or statement is to do refer. And this way, we could just get the specific function or def that we want, which is called from other file. And evaluating the file again, we can call from other file, and that will be true. Now you'll notice that this is linting because we no longer have this alias because I removed it. I mean, to fix it, we could also just add the as again, but at this point, this require vector thing is kind of overkill. Now, this also goes beyond just what's inside your application. I'm not going to import any libraries, So we'll just call one that is provided to us by the core library, and that will just be clojure.string as str, knowing it as s. Let's not get too confused. And here we can now call a string function. So let's do sjoin, which, let me check, collection separated than collection. Okay, we'll join with a space, and the collection is going to be hello and world, and we should expect just the string version of that connected. So there we go. Now you'll notice that this is using a slash, and in other languages you'll see a dot, so dot notation. So in Java it'll be string dot join, then whatever, right? So that is something that you kind of need to get used to, but it's helpful. Now this is also where you could add Java interop. Instead of require, you'll call imports, but it's somewhat the same rules. You get a vector. The only library that I could actually think about right now is Java util, and let's get the UUID library. So there's a small difference. We don't have any keywords here. What we do is we're importing the library, and the second part is the individual classes that we want. We can also do string here, but I don't know if that's inside of Java util, so I'm not gonna risk it. And then you could call any Java method from that Java class. So here, let's just do UUID random UUID. I believe that's the right, and there's our UUID. I was kind of hoping to skip this, but this first part here is a reader symbol. Everything that the hash sign does, it's specific to the reader of Clojure. Hash, and then a type is specifying the Java type. So it's saying that this string is not a string. It's actually a UUID. That's a little bit of an aside, but that's important later when you're more comfortable with Clojure. And there's one last thing I want to mention about namespaces. So these are actually still symbols, even with the slash. And if we were to make a def here to grab the symbol of something, I'm not good with names. Let's just do some symbol. We could do some sim like this. And here you'll see the namespace is prefixing the symbol. If we were to evaluate some sim here, we get just the symbol name because of the quote mark. But if we change this to a backtick, this will fully qualify it, so it'll include the namespace as well. So if we evaluate this again, we get the entire thing. And this is good for a more concrete identifier. So wherever the symbol is actually coming from, the file name or the namespace that it belongs to. Now this also includes keywords, and I guess I'll just call it SumSim again. So if we evaluate this, we get the keyword that we expect it to be, which is SumSim. But if we want to fully qualify it, we could just add another colon. And evaluating this will now give us the entire fully qualified keyword. Now, the thing with keywords is that it doesn't actually have to belong to a namespace. So you can just say something else that pertains to just the meaning of the keyword. So if you want to use the keyword namespace as a categorizer, let's say we have server port and we also have server host. Both of these are valid keywords. Just to show something, let's turn this into a map. Or you know what? Let me put it inside of some symbol. And let's do localhost 9000 and evaluate some symbol again. We get the entire map. Now, once again, this is using the shorthand reader symbol, where it separates out the namespace of the keyword. But if you want to just see it raw, you could add a different namespace in here. So diff. And now we get the map with every single keyword fully qualified as it were. I was really hoping this wouldn't be an hour. There's still a chunk of stuff that I want to cover, but it might have to be in a different video. But there's definitely one thing that I need to cover before this video is over, and that is state. Because so far, everything that has been covered in this video is mostly dealing with pure functions. So we always have the immutable data structure that never changes. But there are oftentimes where you actually want to keep track of changes. And there's 3 different data types for dealing with state changes, or state in general. There's atoms, refs, and agents. I'm going to cover atoms only because I have never touched a ref or an agent. I'm going to make the def inside of the comment, so when I evaluate the file, I don't reevaluate the atom. So this is going to be state, and the atom, you wrap it, and then whatever is inside the atom is going to be the value, the mutable value. So if we were to evaluate state, we get the value of the atom, which is the data type atom at the reference or memory address of this thing. And then the value inside of the atom is nil. Now there's 2 functions that you need to know when dealing with atoms. The first one is reset, which is pretty simple. You just replace the entire atom. And now I'm going to replace it with SumSim, because we already have that evaluated in the REPL. And now if we evaluate state again, we still have the atom. The address doesn't change, so that's the immutable part. But the value inside is this thing. But let's say you actually want just the value inside, and you don't actually care about the memory address. To grab that value out, you use deref. So you're dereferencing the memory address, and this will give you just the value inside, which right now is the map of SumSim. Now there's also a shorthand, which is using the @ sign, and then the atom name. I can't evaluate this way, so I'm just going to add this into a let binding. And there's the atom's value once again. Now you don't always want to use reset, because sometimes you want to actually edit and update what's inside of the atom. And for that, you'll use swap, where you provide the state, and then after that you provide the function and values. So the way swap works is that after the state, or the atom, we provide a function, and then the rest of the arguments that function needs, and that part will be affecting the value of the atom's value. So here, let's try a soak, and we're going to provide a new keyword. Let's just say new keyword, and the value of that new keyword is going to be something new, right? The return type is going to be what the atom now has, and it has new keyword. So far, this is not all that different than using a soak regularly, except when we deref state now, we get that new value. So the value inside of state has actually been updated. But if we evaluate just the atom, it is using the same memory address. So keeping with immutable data structures, the atom itself hasn't changed. It's just what's inside of it. And that's actually it for atoms, but there's still more to learn about Clojure. I just try to make sure to cover as much as I can to get you comfortable with the language. And I hope you enjoyed this video. All right, bye. I'll see you all next time.